All right, today we are going to begin our process of analyzing functions. So the first thing that we want to take a look at is extrema on an interval. Now all this means is the maximum and minimum values. Okay, those are called the extreme values or extrema. Right? Extrema is plural. Singular then would be extremum. So the process used to find these minimum or maximum values is called optimization. So there's times when we want to find the max or the min or both on an entire domain, and other times on just a particular interval. For example, maybe just the positive values. So let's jump right in and take a look at a couple examples of graphs. So on this one, right, this is only defined for x is greater than -1, not including -1 because we have an open dot there, and then this graph goes all the way to where x is equal to 4. So just on this piece of this graph, the absolute maximum value, what's the highest this graph reaches? Well, the highest it reaches is actually right here, right? When we're talking about highest or lowest, we're looking at the y value. So here, 5 is my highest y value. So the absolute max is at the point 4, 5. Okay, and let's just make a little side note that that occurred here at an endpoint. Okay, now what's the absolute minimum across this entire interval? Well, it actually happens right here, right? This is the smallest y value that we reach. That occurs at the point 2, 1. And let's, again, just make a note that that happens on the interval. It's not at one of the endpoints. Okay, let's take a look at this second graph then. Here, we're just defined from x equals -1 to x equals 4 again. So my absolute max looks like it occurs right here. However, this point is not included in my domain, right? It's an open circle. Whenever something like this happens, where the maximum value should happen, we have a hole, we say that there is no absolute maximum value. Okay? That would be the same if we had a hole at a minimum value. For example, if over here on our first example, if this were an open dot, we would say there is no absolute minimum. Okay? So make sure that you pay attention to that. If there is an open dot, wherever the absolute max or the absolute min would occur, we say that there is none. Okay, there is no absolute max. Now, we can get an absolute minimum value from this graph, though. Right? The smallest y value that this graph reaches would be right here at -1, -1. And again, let's just make a little note that that happens not on the interval, at an endpoint. Okay, so let's take a look at a couple more here. So in the third example, here we're just defining our graph between A and B. So here we've got an open dot at A, and then our graph increases forever up here. So when we're talking about absolute max and min, the absolute max, well, this graph just keeps going up forever. And if we have a situation like that, there is, again, no absolute maximum value. Okay, we just keep going up forever. Absolute minimum, then, well, should occur right here. However, we have an open dot there. So again, we say that the absolute minimum value doesn't exist. There is none on this graph. All right. So real quick, you guys try to do this one. All right, so the absolute maximum value on this interval occurs right here, right? And it doesn't matter that this is a cusp. We're not talking about whether this is differentiable or not. All we care about is what is the absolute maximum value on this graph. And it is at the point 3, 2. And let's just make a note that that happens on the interval. Then the absolute minimum, well, it actually would occur at either of these points. However, they are both open circles, so we say there is no absolute minimum value. Okay, so let's put some definitions to relative extrema and absolute extrema. Okay, so take a second and copy these down into your notes. So absolute extrema are what we were just talking about, right? The highest and lowest points on the graph of a function or on a specified domain of the function. Relative extrema, okay, we can talk about relative mins and maxes. Okay, those are like the hills and the valleys of a function. It might not necessarily be the absolute highest and the absolute lowest that we reach, but it's the highest on in a small area, or the lowest in a small area, right? Let's say that it's points on the graph of a function where the function changes from increasing to decreasing, right? So if you need to, you can pause the video to finish copying those down. All right, so here, let's take a look at an example of relative extrema. Okay, here my function keeps going on forever here, keeps going on forever down here. So relative extrema. Actually, let's talk about absolute extrema first. There would be no absolute extrema, right? Because my function increases forever in both directions, right? It goes to positive infinity here, goes to negative infinity here. So there are no absolute extrema, right? No absolute min or absolute max. However, we can talk about relative extrema. Right here would be an example of relative extrema. This would actually be a relative minimum value. All right. So let's see, that looks like that occurs at, I don't know, maybe like negative 1.5, negative 6. All right, so let's say we have a relative min at about negative 1.5, negative 6. I can then say the same thing about this point over here. This would be a relative maximum value because that's the highest point I reach anywhere near there. Okay, it's not my absolute max because this part of the function keeps going up, but it's a relative maximum value. So I can say this relative max occurs at about 1.56. I know that's probably not exact, but close enough. Okay, so let's take a look at this example down here. Now on this one, we're not going off forever in any direction, right? This is only defined from negative 5 to positive 5. Okay, so let's first look for relative extrema. Okay, places where it's either the lowest or the highest point in the localized neighborhood. Okay, so I can say that, right here looks like a relative min, and right here is a relative min. So let's jot those down first. Relative minimum values occur at, let's see, what is that? Negative 3, negative 3, and at 1, negative 5. And then we've got some relative maxes. Looks like that occurs right here and right here. So my relative maximum values are at negative 1, 1, and at 3, 5. Right. Now, here we can talk about absolute extrema, okay, the highest and the lowest points. So we had 2 relative mins and 2 relative maxes. In this case, my absolute max, or let's do absolute min first. So my absolute min occurs at the smallest y value we reach. Looks like down here. Right? So that is the point 1, negative 5. And my absolute max occurs right here. That's the highest y value we reach. So at 3, 5. All right. So let's take a look at the bottom here. Okay, so just asks, considering both functions and their domains, where do the extrema occur? On the interval or at endpoints? Do the relative extrema occur at the function's absolute extrema? So what we can say is that extrema, okay, if we think about all the graphs we've looked at, so I'm going to type this in here. So we can say extrema can occur at endpoints or on the intervals, right? We've looked at examples of both of those things happening. Absolute extremes can be relative extremes. Okay, that happened in our last example there. Right? So if we look at that last function on g of x, right, that relative extrema, so I'll type that out, on g of x, our absolute extrema occurred, did I spell that wrong? Occurred at relative extrema. Okay, so extrema, absolute extrema can occur at endpoints or on the intervals. Okay, relative extrema are just those hills and valleys. All right, so let's go back and look at those same graphs, but let's restrict the domains this time. Okay, so if I just take a look at this graph and I restrict the domain, so I'm saying I'm just going from -2 to +2, right? So I'm saying I'm starting here and ending here, right? So I'm just looking at this piece of the graph. Well, if that's the case, I can talk about absolute extrema. Okay, this value right here would be my absolute minimum value, and this value right here would be my absolute maximum. Right? So let's jot that down. Absolute min occurs at, and we said that was about -1.5, -6. And then my absolute max occurs at the point 1.56. All right, so now it says, well, what if we just look at this function from -1 to 2? So let's put those points in. So now I'm just looking from here to here. Okay, so I'm just looking at this piece of the graph now. Okay, well, my absolute minimum value, the smallest y value that I reach on that piece of the graph, actually occurs here at that endpoint. Right? So I can say that on that interval, my absolute min is at the point -1, -3. My absolute max then is the same as in the first part of the problem, right? My absolute max would still occur right there at the point 1.56. All right, so I want you guys to take a minute and try the next graph. Okay, see if you can come up with the absolute extrema if we're just looking at the graph from -3 to 3, and if we're just looking at the graph from -5 to 2. All right, so if we just look at this graph from -3 to 3, that means I'm starting here and ending here. So the smallest value that I reach on that piece of the graph looks like it would be right here. Right? So my absolute min is at 1, -5, and my absolute max on this interval, so from here to here, looks like it occurs here at the end point. So at the point 3, 5. So now it says let's change what piece of this graph we're looking at. So now I just want to look at the piece from -5 up to 2. So I'm just looking now at this piece of the graph. So the smallest value I reach on this piece looks like it's the same as my first part, right? So my absolute min occurs at 1, -5. My absolute max then looks like it'll be here at this endpoint. Right? That's the highest y value I would reach on this interval. So at -5, 4. Right? So graphically, right, if we're just looking for relative mins or maxes, we're just looking for, where we change from decreasing to increasing or from increasing to decreasing. We're looking for absolute mins or maxes. We're looking for the place where, on an interval, where our function reaches the greatest y value for an absolute max or the lowest y value for an absolute min. So let's kind of bring this all together in this box here at the bottom. There are 3 places where absolute extrema can occur, and we looked at all 3 of them. Right? Absolute extrema can occur. Let me type this in again here. So we can say absolute extrema can occur at 3 different places. First, okay, we saw plenty of examples of this. They can occur at the endpoints of a given interval. Second, they can occur where our derivative is equal to 0, okay, where f prime of x equals 0. And the third place they can occur is where the derivative of our function does not exist. Okay, so let's go back and take a look at those real quick here. So on graphs that we just looked at, right? So if I go back to this one, we looked at a couple of examples where this was a minimum value, this was a maximum value. Those are places where the derivative is equal to 0. Those are places where I would have a horizontal tangent line, right? They also sometimes occurred at endpoints. Right? We said that, well, right here at this endpoint, that was my absolute minimum when we looked at this interval. Now, when we looked at the other graph, okay, sometimes we said our absolute mins or maxes occurred at endpoints, but on a lot of them, we said our absolute mins or maxes occurred at these places. Now, these values here are places where the derivative is not defined, right? These are places where there is a corner. That means the derivative wouldn't be defined there. So we looked at examples, okay, where all 3 of these things happen. So we have to, when we're looking for places where absolute extrema occur, we have to take into account all 3 of these things. The endpoints, where the derivative equals 0, and where the derivative does not exist. Okay. Now, let's take a look at a couple more definitions real quick here. if you want to, I don't know, put a big star next to this one, I think that would be appropriate, right? Critical number is going to be a very, very important definition for the rest of this chapter and really for most of the rest of the year. Okay, a critical number, and I'll type this one in again here. Critical number is an x value of a function All right, so a critical number is an x value of a function. We generally say it's at some value we call c in the domain a is less than, I don't have a good way of writing less than or equal, so I'll just write it like this, or typing it, I guess. A is less than or equal to x is less than or equal to b. So what we're saying is we've got some value c that's in between values a and b, where the derivative at this value is equal to 0, or where the derivative at this value does not exist. So this is basically just saying what we kind of just said in the last box. Okay, a critical number is any value on the domain that we're talking about where the derivative is equal to 0, meaning we have a horizontal tangent, or where the derivative does not exist, meaning we have a corner or a cusp or a vertical tangent or a discontinuity. Okay, so that's what a critical number is. Derivative equals 0, or the derivative is not defined, does not exist. All right. Now, another big key idea, the extreme value theorem. If a function is continuous, that's key. All right, let's underline that. All right. If a function is continuous on a closed interval, what does that mean? Closed interval. Closed means the endpoints are included. Right? So if a function is continuous on a closed interval, and generally we denote our endpoints of that interval a and b, then we'll say our function has at least one absolute maximum and at least one absolute minimum on this closed interval. So if a function is both continuous and on a closed interval, so those are the two things that we need to have, continuous, closed interval, then the function is guaranteed to have at least one absolute max and at least one absolute minimum value. Right? So let's take a look at a few functions real quick and just see if the extreme value theorem would apply. Okay, we're not going to solve anything. We're just going to see if these two conditions are met. Right? It's continuous, and we are talking about a closed interval. So, in this first example, my function is 2x minus 3 over x minus 2. Okay, we just want to figure out if the function is both continuous and closed, meaning the endpoints are included. Okay, so on this interval, from -4 to +4. Well, I want to think about, first, is it continuous? Okay, are there any values that would make this not continuous? Well, sure, right? If I have a 0 in the denominator, well, the value that would give me 0 in the denominator would be a 2. 2 is on this interval, right? 2 is between -4 and 4. So this function, okay, on this interval, we would say that the extreme value theorem doesn't apply, right? And so we can just say extreme value theorem, and we can abbreviate that. It's commonly abbreviated EVT, extreme value theorem. Okay, all caps like that. So we can say EVT doesn't apply because f of x is not continuous let's say it like this. It's not continuous at x equals 2, which is on the interval in question, which is on the interval -4 to 4. All right. The other condition would apply, right? The endpoints are included here, but I need to have both pieces. So this is not continuous, therefore I can't apply the extreme value theorem, meaning we are not guaranteed to have an absolute max and an absolute min on this interval. All right. If we look at the graph of that function, we can clearly see that. Right? If I look from -4 to 4, there's an asymptote here. So I would not have an absolute min or max because this function goes to -infinity here, goes to +infinity here. All right. Let's take a look at our second example. So here, I've got the function e to the x minus 2 plus 1. Okay, so we kind of have to understand what exponential functions look like. Right? Well, an exponential function, I mean, just generally does something like that, right? And obviously, this would be shifted a little bit, but it's not going to change the continuity of the graph at all. So this exponential function, okay, would be continuous on this interval, -5 to 5, and my endpoints would be included. Right? So I can say that I can apply the extreme value theorem here. So I'll say EVT applies for my function g of x on the interval -5 to 5, since g of x is continuous, and let's say for all real values. Okay. Let's take a look at our third example. So here I've got x times the square root of x plus 2. So again, we have to understand domain of functions. Right? Well, I know if I have a square root, I can't have a negative value inside of the square root. Right? So do any of these values here give me a negative value inside of the square root? Okay, well, sure. And if I plug in -6, -6 plus 2 is -4. Right? That would be true of any value all the way up to -2, right? Not including -2. So if I put -2.001 in there, I would get a negative inside of the radical. So here, we would say the extreme value theorem does not apply because h of x is not continuous on this entire interval. Right? So our EVT, our extreme value theorem, is something that you will need to have memorized. Okay, we're going to take a look at a few theorems that you will have to have memorized word for word. Right? And one big thing that they are looking at on AP tests now is that if you're going to apply one of these theorems, okay, the extreme value theorem here, you have to state that you have the two necessary conditions. So here we would have to show that we have our function continuous on the closed interval. Then we can say, well, it has to have at least one max and one min. All right. So let's finish this out with some actual problems here. All right. So what we want to do, right, is what we call the candidates test. All right. We already stated, okay, way back up here. Where was it? Right here. Okay. Where our absolute extrema can occur. Okay. Absolute extrema, meaning either the min or the max, can occur at the endpoints of our given interval, where the derivative equals 0 or where the derivative does not exist. So those are all of the candidates for where an absolute min or max could occur. What we want to do, okay, when we're performing the candidates test, is find where all of those places are. Take the endpoints where the derivative equals 0 and where the derivative is not defined, and test them. Okay, take those values and plug them into my original function and see which one gives me the absolute min and the absolute max. Okay, so let's try an example here. So in A, right, well, I know that my two endpoints are at x equals -1 and x equals 2. Okay, those are two values that I'm going to have to test. I also then want to see what values make my derivative equal to 0. So I need to find my derivative. Right? So prime of x will be 24x squared minus 6x minus 9. So what I want to do is set this equal to 0 and solve. So 0 equals 24x squared minus 6x minus 9. Let's see. Everything here is divisible by 3, so I could divide both sides by 3 to start. So 0 equals 8x squared minus 2x minus 3. So now, let's see if we can factor. Right? If I'm x factoring, I'm looking for values that multiply to -24 that add to -2. Well, I believe -6 and +4 would work. So remember, when a isn't equal to 1, this means we're factoring by grouping. So we would say 0 equals 8x squared minus 6x plus 4x minus 3, and then we group. So we've got, if I group these first two, I can take out a 2x, right? So 2x, and I would be left with 4x minus 3. Then that's exactly what I'm left with here, right? So I'll write that as 1 times 4x minus 3. And then when I finish, I end up with 4x minus 3 times 2x plus 1. Set both of those equal to 0, and I would get x equals 3/4 and x equals 1/2. So what we found, okay, we found that our endpoints are -1 and 2, and the places where the derivative is equal to 0 are at 3/4 and 1/2. There aren't going to be any places where the derivative is undefined, right? This is just a quadratic, so there aren't any corners, cusps, vertical tangents, or discontinuities. So what I want to do now is take all 4 of these values and plug them into my function. Right? So I'm gonna make a chart here. I'm gonna say, here's my x values, here's my f of x values. So I'm plugging in -1, and I'll just write them in order. Oops, and actually I messed up. This should be -1/2, right? we set this equal to 0 and solve. So -1/2, then I'm going to plug in 3/4, and then I'm going to plug in my final value at my endpoint of 2. Okay, those are all my candidates for the absolute min or the absolute max. So I'm going to plug those values in, right? So I'm just going to do this on the calculator. Right? You can do this on the calculator as well. If I plug in -1, I get out 0. If I plug in -1/2, I think I get 4.75. If I plug in 3/4, I get -3.063. And if I plug in 2, I think I get 36. So now what we want to do is look at these y values and just see which one gives me is the greatest and which one is the smallest. Well, -3.063 is going to be the smallest. So my absolute minimum value on this interval, absolute min, occurs at the point 3/4 -3.063. The greatest value then out of these 4 y values is 36. So on this interval, my absolute max occurs at the point 236. Right? Excuse me. So we had our absolute min occurred on the interval, right? 3/4 was in between -1 and 2. And our absolute max occurred at one of the endpoints, at 236, right? So I think what we're actually going to do is try the rest of these in class on Monday. Right? So I will maybe do another one together when we first come into class, and then the rest of them we'll work on together in class, and then maybe a few Math Excel problems. All right. So I will see you in class on Monday.